And I'll put this guy up here. Do I get that guy to go away or no? There he goes. Okay. Beautiful. Okay. All right. Gravel is being dumped into a pile that forms the shape of a cone, whose base diameter is twice the height. If the gravel is being dumped at a rate, so that's going to be a derivative. Gravel being dumped at a rate of 20 cubic feet per minute. How fast is the height of the pile increasing? What about that? How fast is the height of the pile increasing? So that is a rate associated with height. Okay, so the derivative involving height when the pile is 12 feet high. Okay, so it's always increasing. So this 12, I'm going to have to wait till the end because the height is always increasing, but we want the moment in time once that height reaches 12. Okay. What else? The gravel being dumped, a cone shaped here. Does anyone know at least what they're looking for, the relationship of all this? And on the test, I'm going to give it to you. Okay, so I don't want you to feel like you have to know all these formulas. Well, you should at least know some of them, but that's okay. So this is volume of a cone. Okay, volume of a cone. So volume equals, sometimes I have to look, 1/3 pi r squared h. Now, the very first problem on Friday's homework left the 3 variables. And pretty much it's almost, it does seem like it's usually times there. So then we had to use a product rule. But we don't have to leave both r and h because, where is it? Let me do it right. Diameter is twice the height. Diameter is twice the height. So we're going to go off to the side. Diameter is twice the height. Okay, so now, first of all, though, we have an R, not a D. So how do we write diameter in terms of radius? Diameter is twice the radius. So 2R is equal to 2H. Do we see, now this, we're just doing this relationship. You take the radius times 2, you get the diameter. Right? And now this is really nice because what happens when I divide by 2? That was a tricky way for them to say that the radius and the height are the same. Right? On the homework, it's just a little harder, so maybe we'll start that process too. I should have switched them, but of course our book, remember, he gives us the hard one. So we'll see. Now I know how to program. Maybe I'll program it next year. But so I'll start you out on the homework. But these two are the same. So what that means is we can write 1/3 pi. Now, should I put the h in for the r, or should I put something in for the h? But it talks about how fast is the height. So that means I want to leave the h. And so I'm going to put then an h in for the r, and I still have h. You could go either way, but because the question asks about height, I better leave h in there so that I can answer something about the height. Otherwise, I'll answer something about the radius, but it's not asking me about the radius. Does that make sense? Okay, so now we're in good shape because now we can write this as V equals, volume equals 1/3 pi h cubed. When you're multiplying, add those exponents. And now we're ready to go. Now we're going to take the derivative. But what are we doing? The derivative with respect to time, which isn't even on here. So technically the derivative of V is 1, but then I need to take it times the quantity, dV dt, times the derivative of that quantity. We don't really know what the quantity is, but at least I'm showing that I want to take its derivative. All right, remember this is all just a number, coefficient. That's all just a coefficient. So roll it down. So this, let me get my equal in there, 1/3 pi, and then the 3 rolls down and subtract 1. But h is a quantity. So after I do its derivative, I got to take the derivative of the quantity with respect to time. And what about 1/3 and 3? They cancel, right? So we have dv dt equals, we can get rid of those if we want. So we have pi h squared dh. All right, so do we have something about the rate of the volume? Maybe not quite as clear, but the gravel being dumped at a rate, that is forming the cone, and so that is considered the rate of the volume. Maybe that was just a little bit harder to see, but this gravel being dumped at a rate, that forces it to be the rate of the volume. So that's 20. Do we have something about the height? We said the moment in time, the height was the 12, so just make sure we square that. And then hopefully we're finding something about a rate of the height, which I think we already talked about. How fast is the height? So that's the rate of it. All right, that's what, 144 dh dt. So divide both sides by 144 pi. This one, I think this is the one on the homework that says round to 2 places. This could reduce, right? 4 goes into both of those. So, okay, so are we okay? Our answer here is, let me write it like this, 20 over 144 pi. Pi's on the bottom. And then that reduces if we want 5 over 36 pi. And then this says round your answer to 2 decimal places on the homework. So I think it's 0.04. What are the units? Units are, this is height, so it's just a length, so it should be feet per minute. And again, it's kind of nice they give it to us, but it's just kind of a nice reminder of what we found. All right, so any of those are okay? I thought I was going to say something, but all right. So let's take a look. Let's at least address this part on the homework. So if you want to, I know you're just going to have to be able to read it, but, and you can do it again. We won't finish it, but let's take a look at the homework. Okay. So gravel is being dumped from a conveyor belt at a rate of 15 cubic feet per minute. Its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 9 feet high? So they feel like the cone is based off of like what you're pouring. Is it sand? Is it fine sand? Is it gravel? Is it stone? That kind of determines supposedly the shape of, kind of the shape of the cone, right? And have you ever gone by, like, if you're from around here, like we have those domes of gravel, or not domes of gravel, salt, right? And it doesn't go up. It's not, we don't pour it, we don't store it in a cylinder, because when they pour it, it forms a cone. They're not perfect cone shapes, but if you're driving on the toll road, you'll see next time it's more, comes up to a point a little bit more, because that's how sand gets poured. All right, and I always want to take a picture, but we're driving by the tollway. I'm like, I need a picture. Forgot, but one of these, you know what? I probably should Google it. I probably could Google it. Yeah, my time. All right. Okay, so let's see. This is volume. Okay, so volume was, what was it? Let's see. Actually, let's yeah. Okay, this is okay. 1/3 pi r squared h. Okay, so that's for volume of a cone. Volume of a cone. Okay. So maybe he makes it easier to type. He typed that the diameter and the height are always equal. So that's easy enough, but we want the diameter in terms of the radius. So we're going to do 2r is equal to h. But now we wanted to plug in something for R. Okay, we definitely, this would be nice to plug it in right here for H, but I think it asks for something about the height, right? How fast is the height? So I think we're going to actually have to solve this for R. And so we're going to have to put in H over 2, which makes it a little bit harder. It actually turns out okay, but let's, okay. All right, so let's go volume equals 1/3 pi, and we're putting in H over 2, and then we got to square that times the height. Okay on that. Same thing we just did, except it just wasn't a nice plug-in, right? We're plugging in, instead of H, we got to plug in H over 2. All right, so let's just do a little bit of algebra. This is 1/3 pi. This would be H squared over 4. You square both the numerator and the denominator. All right, and then what does that equal? That equals, it's okay to multiply the 3, because all this is all multiplication, so it's okay to multiply the 3 and the 4. So we're going to do 1/12 pi, and then H to the 3rd. So we can multiply the 3 and the 4, and then we can multiply the H squared with the H and get to the H third. Yeah, so now I'll let you finish that off from there. This is what we had, and the one in the notes just didn't have that extra 4 on the bottom. Yeah, so it was right here. So it just had 1/3 instead of 1/12. Okay, but same thing. So you can kind of work from there. And it does say, Roger, answered in 2 decimal places, so go ahead and go with the decimal. If we have time at the end, we can finish, but let's try a few more. But this was just a little bit harder. But the good thing is it eliminated a variable, which is a huge plus. All right, we'll leave that there. We can come back to it. All right, let's try a few more. Some of these are so standard. Like every book has them. I don't know why they didn't program more of these into WebAssign, because they're so easy for them just to type. But all right, here we go. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Now, keep in mind, I realize you've only read this one time. Let's try to get a picture. And I realize that's probably the hardest part. So, spend a little time if you need to, because once you get going, it's not too bad. Okay, so we've got a wall, and then we have the ground. And we have a ladder. Too much color, but this guy is the ladder. Okay. And you know how you lean it against it, and this might not, maybe this is an over exaggeration, but you know how when you lean it, right, you don't keep it vertical, it's at least at some angle. Okay. So again, I just kind of made it so we had a triangle that we could work with. But even if it's just coming down to here, it's still forming a triangle. The ladder is the blue, and it's 10 feet long. Now, no matter what happens in that problem, is the length of the ladder going to change? No. So that's something that we'll be able to use right away. Okay. This, all right, let's see, what else does it say? Okay, now how fast is the top of the ladder sliding down the wall when the bottom of the ladder is at 6 feet? So this distance is always moving because it's sliding, but we want to know when it's 6 feet. So maybe I'll put it like in parentheses. That's always changing, but we're talking about the moment in time is when it's 6 feet. Okay. And let's see, the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So we're also talking about this, the bottom of the ladder sliding away from the wall. The rate is 1 foot per second. Okay, any ideas what equation we're going to use? The first thing, now that we kind of have the picture, what's the equation we're going to use? We're talking about a right triangle. Hopefully they even said a vertical wall. So we're going to do Pythagorean theorem. Okay, a squared plus b squared equals c squared. And what's the piece of information that we can plug in right away? We can plug in the 10 because that's never changing, and that's the hypotenuse. So we're going to do a squared plus b squared equals 10 squared. Right, and then 10 squared is 100. I think we're ready to go. All right, so what is the derivative of this guy? Beautiful, yeah, roll it down, 2a, and then we have to take the derivative of that quantity because we want to do the derivative of a with respect to time. And then we get to practice it again. We're going to roll it down, subtract 1, so 2b, but then db, in terms of time, db dt. Question on that. Don't forget that. If you forget, if you don't forget that, then you're in good shape. Derivative of 100 is 0. And you don't even have to change, like if this is a weird number and you don't know it, you can leave it squared. Just don't make sure that you don't roll down the 2. Don't roll it down on a constant, okay? 10 squared is still a constant. So even if you don't change it to 100, it goes to 0. All right, let's see, what do we know? We know the moment in time, this guy is 6. What do we want to call that? Let's show up. We'll call this A and this B. All right, so we know that we got the 2, we got the B is 6, and actually we know its rate. What is its rate? 1. Okay, so now over here, the only problem is, here's our plus. Let's put our plus here. Are we looking for A or are we looking for the rate? How fast? That means we're looking for the rate, okay? And does that make sense? The top of the ladder is going down. Okay, and that's exactly what it says. How fast is the top of the ladder sliding down? This one's going out, this one's going down. So that means we're looking for dA dt. We're looking for a rate. Beautiful. How do we find A? This is the only hard part, or the part you have to remember for the Pythagorean theorem. At that moment in time, we can do a squared plus b squared equals c squared. And we can go find A by plugging in the 6 and plugging in the 10. So don't forget, you can find A by go ahead, because now once I've taken the derivative, then I can use the 6 again. That's fine. Okay. I can't remember. I think this one turns out okay, but on the homework, it might be a radical. See, I got this from another book. Those other books are a little bit nicer. Is this 64? So that gives us 8, the square. So to undo a square, remember that's what a squared is. So to undo a square, take the square root. And so A equals 8. Okay, so now we just have to solve this for dA dt. So we'll do 16 times dA dt plus 12 equals 0. So kind of a weird answer, so let's talk about it once we get there, right? Subtract 12. 16 BA dt equals negative 12. And then divide both sides by 16. Why is this a weird answer? It's negative. And then we can simplify it to 12 over 16, so that goes in there, what, 4 goes into both, so 3/4. The first 3 answers on your homework are negative. Is negative okay? Yeah, because remember, rate, it's really dealing with like velocity, right? And so it is how fast. Does it make sense that the negative is just correlating with it going down? So the negative is more than okay, just showing you that it's going down. Remember, velocity is kind of like speed with direction. So don't let that bother you at all. And then it's feet per. So if the rate of this is feet per second, the other rate has to be feet per second. So that was a little interesting twist there. All right. Let's do at least a few more. Wish I put it right today. Oh. Okay. All right. A spherical balloon is to be deflated so that its surface area decreases at a constant rate of 15 square centimeters per minute. At what rate is the diameter decreasing when the diameter is 18? Okay, this one, we're dealing with a sphere, but it's not volume. Don't get too far ahead. This one isn't volume, this is surface area. All right, so just one more equation. So like I said, you don't have to memorize them, because I don't want you worrying about all that. We've got enough rules to memorize, okay? So, all right, so surface area. It is, and I'll just do A for area, surface area, is 4 pi r squared. Now we have just a little bit of trouble because that's a formula for area, but remember I'm supposed to relate everything in the problem. What are they actually talking about in the problem? They're talking about the diameter. So remember, I want to put a D here, but they're related, right? The diameter is 2r. So it's just a little, now in the homework, you won't have to do this. The homework, just be careful. The homework talks about the rate of the radius, which is great, but it gives you the diameter. But in that situation, you just have to take the diameter, divide it by 2, and you just get to leave the r in the problem. Okay? So just be aware, they didn't make it quite as hard, so just take advantage of that, but you still have to take the diameter, divide it by 2, and then just stick with the radius. Here, we're gonna have to plug in d over 2 for r. So we've got area equals 4 pi, instead of radius, we're gonna do the diameter divided by 2. And that makes sense, right? Because if you were talking to someone, you would say, hey, the radius is the same thing as the diameter divided by 2. This one, okay, this one turns out kind of nice. Let's go ahead, before we even take the derivative, we can bring this in. So d squared over 2 squared, which is 4. And that turns out really nice because then the 4's cancel. So that turned out okay. That one was a little trickier, but it, oh, we canceled the 4's, hang on. We cancel the 4, so we actually really only have pi times diameter squared, because the 4's cancel. All right, and now we're ready. We kind of did it any cleanup we needed to. We've got our area, we got our diameter. Take the derivative. Okay. Derivative of A is 1, but then times the quantity, so dA dt. And then this guy, roll it down, subtract 1, and then times the derivative of the quantity, dd dt. All right, let's see, what do we know? What is the rate? At what rate is the diameter decreasing? So we're looking for diameter's rate. Okay. Surface area's rate. Surface area's rate is 15. Okay, so surface area's rate is 15. Do we have the length of the diameter at that moment in time? Diameter is 18. Now, we should probably, and again, we can argue, you know, if it's a rate, should it really be negative, things like that. But I think, and I just got it out of a book, so I think this one, does anyone understand why this should be negative? Why would that 15 be negative? Yeah, it's the rate, but it is being deflated. So it is actually decreasing. Okay. Look for it. I'll tell you right up front, the first 3 on your homework are negative. Okay, and one, I think the first one's like this. So if it's talking about deflating, then we really should put in a negative. All right, other than that, we're good. That gives us what, 36? Let's leave it on there. Well, let's at least, let me put it here. That gives us what, 36 pi dd dt, and then divide by 36 pi. Let's keep it on there. Hopefully we can see it. All right, it's a little messy here, but so negative 15 over 36 pi. I don't know if it asked for, I think this one might be this answer, that's fine. It can reduce though, so 3 goes into it, right? Yep, 5 and then 12. I'm not sure it's gonna save you any time at all, but instead of going to the right and finding the pi symbol, if you just type the letters pi, it'll change to a pi symbol. So as you're typing, you're gonna have to go over there for the fraction bar anyways, but if you ever just remember you wanna just do pi, pi will pop up. Good. Does it make sense that this rate is negative? Yeah, right, because it's shrinking, so that rate, what was it, the diameter? But the diameter is shrinking as well, so that actually correlates that. That works. All right, let's see if we can get through 2 more, and then that'll be good. This one's 4 isn't too bad. 4 will be quicker. So let's try 3. Take this off. Oh, actually, I'm supposed to do that. Okay. All right, a baseball diamond is a square with sides of 90 feet in length. A batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate, now this is a little weird, at what rate is this distance from second base decreasing when he is halfway to first base? Okay, so do we have any softball or baseball players? The one on the homework is softball, so someone. All right, so we got this guy running. At a moment in time, we stop, and they want to know how his rate from second base, which makes a nice right triangle there, okay? Depending on how good I draw it. If I should this way. So just notice that they're talking about from second base. So here's my right triangle. Now, he's running, so this distance is always changing, but they want us to stop when he is it this one? When he is halfway. So what would this length be? It's always changing, but the moment in time it is halfway or 45. Okay, but that one's always changing, so I'm going to put it in my parentheses. There's one though that's never changing. This is always going to, my red line's going to always be changing too, right? Because originally he was here, then he's running here. So that distance or that line is always changing. But the distance, hopefully, right, guys, the distance from first to second never changes. Now, I guess you could say like, it could change if we're talking about him running. But as of right now, we're literally just talking about the bases from first to second. So this is 90, and that guy's never going to change. So he rounds first, all right? He's not there yet, he's halfway. Okay, so what are we gonna use? We got a right triangle, we're talking about the sides. Pythagorean theorem, okay? A squared plus b squared equals c squared. All right, we'll call the 45A, but the 45 is always changing, so we're gonna have to leave that. But the B is 90, and we can plug that in right away because that's never changing. And that gives us what? 8,100. But in the end, it doesn't really matter if you got it wrong because we're going to take the derivative of a constant, which goes to 0. I think we're ready to take the derivative. So roll it down, subtract 1. But just remember, we're doing it in terms of t. So then it's got to be dA dt. The derivative of that constant goes to 0. And then remember, don't forget, it's 2c, but we're doing it in terms of time. So dc dt. Good, all right, what do we know? Now the moment in time, now we can plug in the 45. Do we know the rate? The rate, it deals with him running, so that would be this side as well. And that is the speed, or his rate is the 24. I think this one, and again, yeah, this one, okay, whatever book I got it from. This 45, is this guy? Yeah, this 45, is that increasing or decreasing? He's running towards the base, so this is going to be decreasing. So this guy should really be negative 45. All right, and then we've got 2. We're looking for the rate. So this guy's going to stay. We're looking for the rate. How do we find C? Don't forget, we can go back and do a squared plus b squared equals c squared, because now I can use 45. All right, so we know a squared is 45, or a is 45. B, actually, we know too, don't we? B is 90. And then we're actually looking for C, which is good because checked it out. That's what we're looking for. This is what, 2025. This one is 8,100. So when we add, we get a pretty big number, 10,125. You can definitely simplify, but I believe this one, oh, that's what it looks like. On the homework, I think it says to round. I'm pretty sure this says to round. So we're going to take the square root of both sides. And again, we could simplify it. It's not a perfect square, so we could also, let's just leave it. It's a big number, but that's okay. The only negative side is I didn't leave enough room. Let's see if we can sneak it on here. And 120. Good, and then it's just a matter of dividing that and then typing it into your calculator. If you want to do some simplifying here, you could cancel the 2's, make that maybe a little bit easier. Did anyone try it? I think I got 10.733. So we want to do, and actually it should be negative, right? Now, does that make sense too? Would this distance be decreasing? Do you see how that distance would be decreasing? Because here it would be that longer and he's running. So that distance is shortening up as well. But we're just talking about the rate. What was I going to do? 45 times 24, and then divided by the square root. Okay. All right, let's do the last one. Oh, should we do that one or? Okay. The volume of a cube is increasing at a rate of the volume, and that's actually pretty small for volume. So this answer is actually really small, but increasing a volume of only 10 cubic centimeters per minute. Right? How fast is the length of the sides increasing when the length of an edge is 30 centimeters? How do you find volume of a cube? This is a nice one. You probably should have done this one first. You do length times width times height, but of a cube, what do we know about the length, the width, and the height? They're all the same, right? A cube means that they're all exactly the same. So we could just put, I just wrote L3. We could do S3 if you want, or E like for edge. They're all the same. So we have two variables. We have, this is a moment at time, and this is a rate, but we only have two variables to begin with. So I think we can go ahead and take the derivative right away. I kind of like this one because this one you have to go, okay, it's 1, but then it's times the derivative of the quantity with respect to t. And then this one you have to do a little bit, right? You have to roll it down, subtract 1, but you have to remember that in L is time as well. So dl dt. So that's like a perfect one. You got this, you got this, you don't have anything to plug in at the beginning. Okay, so and it states right away the volume has a rate of 10. The volume has a rate of 10. So there's our 10 for our volume. And then the length of the edge is 30. It's always increasing, but our moment in time, it is 30. So 30, and then we have to square it. So hopefully, is it asking something? Don't even look at the question. If my dl dt is what's like my variable, and that's what I'm solving for, what is that standing for? The rate of the length. The rate of the length. So is it asking for something? How fast is the length? There it is. How fast is the length? Good. So yeah, so now it's like I said, it's a pretty small number, and that's okay. That would be what, 30 times 900. That would be what, 2,700. And then divide, it gets a little bit smaller, right? Because when we divide, are we okay? And then when we divide that, just multiply that out. If you have a calculator, you could do this all together. You don't have to do 2 steps if you don't want. Absolutely, that's okay. That cancels 1 over 270. This is just an edge, so this is just a length. So it would be centimeters per minute. All right, 5 and 6, let me just show you. I just want to show you. The setup for 5, we're actually talking about an angle. Can you kind of see it? Let me see it. We're actually talking about an angle changing, and we actually use SOHCAHTOA. So you can also do things with that, but don't worry about that. This one's really hard. I think I put this on. I think I put that on, but that's extra credit anyways. So you have plenty to do anyways. You have the gravel one now from Fridays, and then 1 through 4 on tonight's, and 5 and 6 I left extra credit. If you have some time this week and you want to look at it, that's fine, but don't worry about it, okay? Eventually I may take those off anyways, but so 1 through 4, but don't also forget about your gravel. So that's one. Okay. And remember, I think it's 1 through 3, they're all negative because something's decreasing in 1 through 3, okay? All right, tomorrow we're just gonna reapply something we already know, and then Wednesday and Thursday review, okay? So make sure if you have questions, as much as I want you to work on this, and there will be one of these on the test, you got to know the derivative rules, okay? So if you're stuck on that worksheet, make sure you see me, okay? Because when I hand you the review on Wednesday, you're going to think you got the review that I gave you last Wednesday, okay? There's just, I think, 2 word problems and the thing that we're doing tomorrow. Okay?